Hello everyone, I'm Murad from Elisa Konovago Lab at Columbia University, and today I'll be talking about a new method to assess fast induced lesion size using multi-frequency single transducer harmonic motion imaging. Fast ablation technique has been applied to different kind of diseases. A successful ablation depends on its monitoring and the lesion size assessment post-monitoring. To monitor fast treatment, magnetic resonance imaging guided fast and ultrasound imaging guided fast has been used. In MRI guided fast, uh, monitoring is performed by monitoring the temperature rise during treatment. In ultrasound imaging guided fast, the changes in echogenicity is observed to monitor fast treatment. In our lab, we have developed a harmonic motion imaging guided fast to monitor a fast ablation treatment. In HMI guided fast, a imaging transducer is inserted in the opening of the fast transducer, and the imaging transducer is used to monitor displacement, oscillatory displacement during the treatment. And from the oscillatory treatment, the monitoring is performed. In addition to the monitoring, assessment of the lesion size is very important. So we have to know how much we ablated, whether we are ablated the whole tumor volume or partial tumor volume, and how the tumor changes over time. To monitor the FUS fast treatment, lesion size, we are developing single transducer harmonic motion imaging using a standard uh, ultrasound imaging system. In STHMI, the voltage or amplitude remain fixed, and the single imaging transducer is used to track and to induce and track oscillatory motion. In STHMI, the voltage or the amplitude remains same, and then the duration of the discrete excitation pulse are changed to generate a oscillatory motion. Here is example of 220 Hz. Then the tracking pulse are interleaved between the discrete excitation pulse to generate to track the oscillatory motion. And this excitation and the tracking pulse are implemented in a focus excitation and the tracking beam. And to generate a 2D image, a moving walking aperture beam sequence is implemented electronically. And the imaging is very robust against motion artifact, because we know the oscillation frequency, which can be easily filter it out from the other motion artifact. And the acquisition time is very short and less than 2 seconds, because everything is done electronically. And so another advantage is that we can exploit the oscillation frequency to detect different size inclusion. Here is an example of larger versus smaller inclusion. For a larger inclusion, all the frequency performs similarly, while for a smaller inclusion, only detected by the higher frequency. These images are peak-to-peak normalized displacement image. Normalization is performed with respect to the background. However, in this case, all the frequency are collected separately, which may not be feasible in clinical setting due to the registration problem, or due to the collection of the time, a longer collection time. To reduce the time, we recently developed a multi-frequency single transducer harmonic motion imaging. In multi-frequency STHMI, the excitation pulse composed of sum of sinusoid with target frequency. Here is a continuous excitation pulse composed of frequency from 100 to 1000 Hertz. Then this continuous excitation pulse was sample to transmit the discrete excitation pulse, and similar to our previous work, the tracking pulses was interleaved in between the discrete excitation pulse. So in this way, we can collect the data from 100 to 1000 Hertz in a single acquisition. Only the data are processed differently to separate all this motion image. So the objective of this work to develop a standard ultrasound system with the imaging transducer to generate or to assess FUS lesion with different sizes without prior knowledge by collecting multi-frequency displacement image in a single acquisition. Here is our experimental parameter. Here is a FUS parameter. We change the duration and the lesion number to create different size of lesion. And here is our multi-frequency STHMI parameter. STHMI is performed using L74 with a Verasonics Vantage ultrasound system. As the L74 is larger than the opening of the FUS transducer. For this experiment, we also use P12.5, which is inserted inside the opening of the FUS transducer to match the plane between FUS ablation plane and the STHMI imaging plane. We created total 7 different lesions with different sizes in chicken and swine muscle. Here is our experimental setup. We use two metallic pin to match the plane between FUS and L74. And here is the B-mode image used from the P12.5, and you can clearly see the two metallic pin. And then the ablation was performed. And after ablation is done, we moved the transducer to image with L74 for STHMI, and you can clearly see the metallic plane. Then after the STHMI is done, we also use gross pathology to determine the size of the ablation and compare with STHMI displacement derived size. To quantify the size, we use a simple algorithm. Here is a example peak-to-peak displacement image at 600 Hz. Again, all the images are shown normalized, and the normalized with respect to the non-ablated region. So then the pixel this image are converted to an image with pixel ranges from 0 to 1. Then we perform threshold of 0.5. You can think of that as like full width half max, and then the thresholded area will give you the ablation size. And we perform similar in the gross pathology images, and then the area in the displacement image will be compared with area with gross pathology images. Here is the example lesion with 3 minute of duration, and here is the B-mode image. In the B-mode image, you cannot see the presence of the B-mode cannot detect the lesion size. Whereas in the gross pathology, you can see that the lesion was 10 by 15, 16 millimeter ish, and all the displacement image show that there is a low displacing or the stiffer ablated region. However, if you look at the CNR at the title of the images, you can see that from 300 to 900 Hz perform similarly compared to and their performance was better than compared to the 100 Hz or 1000 Hz. So for a larger larger lesion size, we can say that most of the frequency performs similarly. However, when the duration was smaller, 40 seconds, you can see that the lesion size was smaller. Again, the B-mode was not able to detect the presence of lesion. However, if you look at the higher frequency displacement image, you can see that it clearly detects the presence of lesion. So for a smaller lesion, the higher frequency was better. So this result suggests that without a priori knowledge of the lesion, we can use this kind of multi-frequency acquisition to collect all the frequency from 100 to 1000 Hz in a single acquisition. Then we can use to detect different size lesion. Here is a correlation of STHMI derived area versus gross pathology area for 700 Hz, and you can see that the size of the lesion varied from 20 millimeter square to 140 millimeter square, and you can see that like the 700 Hz show very good correlation with R square of 0.96 and the root mean square error of 9.5 millimeter square. And this is the example at only for 700 Hz. And here is the regression parameter for R square was always greater than 0.9 for frequency from 200 to 1000 Hz, and the root mean square error was less than 15 millimeter square for frequency for 400 to 1000 Hz, and the lowest root mean square were observed at 700 Hz. So in conclusion, in this work, we show that STHMI can detect a lesion of different sizes from 20 to 144 millimeter square by collecting data simultaneously from 100 to 1000 Hz. For a larger lesion, all the frequency performs similarly, whereas frequency higher than 600 Hz was better for detecting a smaller lesion. STHMI-derived area was highly correlated with area from the gross pathology with R square greater than 0.9 to an RMSC less than 15 millimeter square. So in this work, each image was used to individually calculate the area of the lesion. However, we can combine the displacement images from all these frequency to improve the performance. So future work will generate an algorithm by combining STHMI images and automate the process. And we also implement STHMI in a phased array so that we don't need to move the transducer, and we can quickly perform the lesion size assessment just after the FUS ablation. And also we will perform validation of our technique in mouse and the human breast tumor with a histopathological validation. I would like to thank our funding sources and my lab mate. Now, thank you for your attention.